Hey everyone. So the last meeting recording cut out, so I'm just going to finish up with the free response, and then I have to go. Completely fine, but I'm just going to finish up. So I'm just going to search up the ones that have 7.3 because we did a lot of problems from 7.1, 7.2 last time, so you can check that out. But let me see if I can find 7.3. So anything that deals with elementary particles, let's see, nothing there. I'll search up quark. I'm sure something will come up. Okay, good. Good. So we found one with the Feynman diagram showing electron capture, and then what we do. So Feynman diagram shows electron capture. Deduce that X must be an electron neutrino. So what's happening here? This looks to me. Wait, no, that's a plus. So a proton is becoming a neutron. So it looks like a proton and electron are coming together. And what you get back is a neutron and X. The X has to be an electron neutrino. But why? Probably because of conservation of lepton number. I would think so. Reason, I think for this one, I would say conservation of lepton number and baryon number, because what's happening is you have a proton, you have a neutron, and that's becoming you have a proton and an electron, and that's becoming, on the right-hand side, you have a neutron, and then you have X, whatever X is. So if you have X, baryon number-wise, baryon number, so for B, baryon number, proton is 1, that's 0, that's 1. So that also has to be 0 to conserve baryon number. Lepton number, I don't know if that's called L, but I'm just going to go with that. That's going to be 0. That has to be 1, because all leptons have a lepton number of 1. That's 0. And that also has to be a 1. And charge, that's another good thing. That's 1 plus, and this is 1 minus, and this is 0. So 0 on the left-hand side almost also means 0 on the right. So the only particle that I know of on our list of leptons that have 0 baryon number, so it has to be a lepton because there's 1 lepton number, that has 1 lepton number and 0 charge are all the electron. So these are all your neutrinos. The mu neutrino could be it. It could be muon neutrino, electron neutrino, muon neutrino, or tau neutrino. But we also have to conserve, and then the last thing I would mention in the response is that it has to conserve generation or family, right? So if it's first generation, if it's electron, then it also has to be electron. That's why I would use that instead. Let's see what they put in there. Yep, so it has lepton number of 1, and then it has a charge of 0, or it has a baryon number of 0. So good. Okay, distinguish between hadrons and leptons. So that's just by definition. Hadrons are made up of quarks and or antiquarks, and hadrons interact with strong force, whereas leptons are simply leptons are smaller, lighter particles, and also leptons are fundamental particles, whereas hadrons are composite. They're made up of quarks, so they're not fundamental. What else would I put? I think that's sufficient for the point. Let's see. So hadrons experience strong force, as we said, or leptons do not experience. That's the first mark. And then the second, let's see. Then hadrons are made of quarks, are not fundamental, exactly, and leptons are not made of quarks, are fundamental. Good, as we said. And then, I don't know if it's 3 marks. I don't know how the marks are distributed, but we got the first 2. And for this one, hadrons eventually decay into protons. I did not know that. Apparently that's the case. So hadrons eventually decay into protons, and leptons do not decay into protons. Obviously, because leptons are fundamental, so they can't break it down. Okay. Let me see if I can find another one with a quark. Okay. Is that just the next question on there? No. Okay. Let's look at this question here. So a possible decay of a lambda particle is shown in the Feynman diagram. So up becomes up, down stays down, then strange becomes up, which is interesting. Okay. So strange becomes up, and in that process, we have an anti-up and a down, and that's a negative pi. Okay, state the quark structures of a meson and a baryon. So a meson is so these are both hadrons, okay, because they both have quarks. Mesons are made up of a quark and an anti-quark, right? The meson is a quark anti-quark pair, and then baryons are made up of 3 quarks. Yep, good. Explain which interaction is responsible for this decay. Okay, so is it going to be W minus, W plus, or Z0? So how do you determine that? That's where I struggle a little bit, but let me think. So charge-wise, I think we have to think about charge. So strange has a charge of negative 1/3, and then up has a charge of 2/3 E. I'm just going to disregard the E for now. And then down, I believe this then has to be W plus, because that W plus, the 1 minus the 1/3 will get you to the 2/3. I believe so. Because also, let's check here. Anti-up would be 2/3, because up is 2/3, so anti-up I assume would also be 2/3 charge, right? And then down would have negative 1/3. So same idea, 1 minus 1/3 is 2. Okay, so I think it's W plus because of that. So we have to explain, and so strange quark changes flavor to an up quark, as we said, and then that only happens by the weak interaction, like we said. So it's W. Oh, so you don't have to say whether it's W plus or W minus. So you should have. I guess I would have actually gotten that wrong, maybe. So you would have had to mention weak interaction. Okay, changes in quarks happen only by the weak interaction, which is what we know, like beta minus decay and beta plus decay. So that's weak interaction. Okay, draw arrowheads on the lines representing anti-up and down. So anti-up has to be to the left, I believe, because it's an anti-particle, right? So it has to be to the left, and then down can go to the right. So it's left and then right. Yep, exactly like we showed. Good. And then identify the exchange particle. Okay, so interaction was weak interaction. Now we have to identify the exchange particle. So as we said, strange, according to our chart, is negative 1/3. This is positive 2/3. So this is, did I say weak plus before? If I said W plus, that's probably wrong. I think I got that wrong. I think that would have been, it has to be W minus. Because if negative 1/3 is coming in, and that goes to 2/3 and minus 1, yeah. I think whatever's coming in has to equal this plus this, whatever's going out. So 2/3 and minus 1 gets to minus 1/3. So I guess similarly, if I have the anti-up would be 2/3, and this would be minus 1/3. So W minus would equal 2/3, or W minus and then 2/3 would equal minus 1/3. Yeah, I think it's W minus. It is W minus. Yeah, W plus would be correct. It has to do with conservation. I'm not entirely clear on this, but I think the way to do it is to check, well, up has 2/3, strange has negative 1/3. So then if 1/3 has to be conserved, so negative 1/3, I mean, if I have a 2/3 here, that has to be minus 1. Similarly, if I have minus 1 here and 2/3 is coming in, then that produces. Yes. Okay. All right. And then outline one benefit of international cooperation in the construction or use of high energy particle accelerators. So that's kind of, it's a very weird question to me at least. But one benefit of international cooperation, the cost is, it's very expensive to build these high energy particle centers. So if it's international cooperation, the cost bared by each country is lower. So less burden, less financial burden on each country. That's what I would. Yeah, lowers the cost of individual nations. There you go. International understanding, historical example. This seems like more of a, or anyone. That's funny. That seems like more of a history question to me than a physics question. But okay. All right. So let me see if what other questions have the word quark in them. Okay. Particular K meson has a quark structure anti-up S. State this charge on this meson. Well, that's just a data booklet. So anti-up has 2/3. So I assume anti-up also has 2/3. And then the charge, and then strange has a charge of -1/3. So I assume the charge is 1/3 on this meson. Can a meson have 1/3 charge though? Let me check. I might be, it's -1. That's wrong. Why is that? Oh, I think I misunderstood this. So anti-up, okay, that's right. Anti-particles have the opposite numbers. So if I have, I see. If I have up, if up has a charge of 2/3 E, then anti-up will have a charge of -2/3 E. And then strange has a charge of -1/3 E. Then that gets you to minus. So then the previous question that I did was also wrong, or not wrong, but part of it was misunderstood. Let me go back and make sure I fix that. So here, let me go back to this diagram. So strange was -1/3, up was +2/3, and then so that's still W minus because we need -1/3 has to equal 2/3 -1. And then anti-up will be -2/3, down will be -1/3. So whatever comes, the sum of these two, because that's what's being emitted, right, has to come from this intersection. I believe so. Okay. Yeah. Because that, if that was W plus, that would be problematic. That can't be true because W plus would not conserve the. So that's okay. All right. Going back. So now this Feynman diagram shows changes that occur during beta minus decay. Now label the diagram by forming some particles. So you have up. Neutron is made up of up, down, down. A proton is up, down, up. Okay, so now what else? We're gonna have some weak interaction here. So W either minus or plus, and then here during beta minus decay, we have an electron emitted. So we have an electron neutrino, and then same idea. Down has a charge of -1/3, and then up has a charge of +2/3. So that has to be -1/3 is 2/3 -1, so that has to be W minus. And then also we can check by saying, well, an electron is -1, and that has charge 0, so obviously that also has to be -1. W minus. Okay, so I believe it's down, up, weak minus, and electron. Down, up, weak minus, electron. Good. Okay. Now, carbon-14 is a radioactive isotope, undergoes that energy release. I explained what the mass of the carbon-14 nucleus and the mass are slightly different, even though they have the same nucleon number. Well, because they have different binding energies, because they have different binding energies, because due to the different number of protons, there's a mass defect, right? The strong nuclear force acts stronger on one of them, I guess. So because of the greater number, I think N14 will have, nitrogen has more protons. I don't know which one has more protons, but either way, It goes beta minus. So yeah, nitrogen 14 should have more protons. So if that's the case, then nitrogen 14 probably has strong nuclear force acting. I don't know. Something along those lines. Maybe the explanation is that the mass defect is different. They have the same nuclear number. Well, so I guess the difference is that they have different proton numbers. So because of the different proton numbers, the strong nuclear force acts differently on them. I don't know. Let's see what they say. Decay products include an electron that has mass. Oh, okay. Electron products have energy that has a mass equivalent. Mass defect was converted to mass or energy of decay products. So the mass of carbon 14. Oh, mass of carbon 14 is greater than the mass of neutron 14. Okay, let me see. With carbon 14, C14 is undergoing beta minus decay to produce N14. Beta minus that's becoming beta minus, and this is carbon has 6 protons, I think. Anyways, carbon has 6 protons, 6, and it'll be 7. So 7 minus 6, and that's 0, and then of course we have our but that's the case. Nitrogen does have more protons, so I don't get this. Let's see. The mass. Okay, I see. But this also, the masses are different because carbon 14 initially had all the mass. That mass gets converted into mass of nitrogen and the mass of an electron. Because the electron occupies mass, the nitrogen mass is going to be less than the carbon mass. So say you started off with 3 beads here that could represents the mass. Let's say a small portion of that bead goes to the beta, then you're left with 2, and then mostly 3, but a small portion is taken away for the beta minus particle. So that's why nitrogen mass is less than carbon 14. That's how I would say, because I think that's the easiest way to do it. But now these other 2 explanations I don't really get. Proton has protons. Products have energy that has a mass equivalent. Yeah, but I don't know how that answers the question. A mass defect is converted to mass of decay products. That's kind of what we were saying, but in a more sophisticated form. Okay. Anyways, that answers that question. Let's see now. Think. Okay, this is like a half-life question. I'm just going to see this last part here. So quarks were hypothesized long before their existence was experimentally verified. Discuss the reasons why physicists developed a theory that involved quarks. That is an interesting question. Well, because of conservation laws and stuff, it needed to match, and also probably because the mass. I don't know how. I guess why we need a theory that involves quarks. Why would we need that? Yeah, I would think because of conservation of certain numbers of some sort. Occam's razor. What? This is a very weird explanation. Quark theory is simpler, or a simple model explains complex observations. So basically, they were just looking for a simpler theory. Okay, so apparently that's a reason. All right, so one is that there's a quark theory is simpler, so we need a simpler theory. And oh, good. So we talked about conservation rules. Maybe we would have gotten one of the 3 points. Model incorporates conservation rules. Quark theory is simpler would have been another point, I guess. Model incorporates strong and weak interaction forces between protons and neutrons. Okay, so basically we needed quarks to better understand the interactions between nucleons. And we also need a model that explains differences between neutrons and protons. So yeah, why exactly are neutrons and protons different? What makes them different? So yeah, I guess if we push a little bit further, we could find that out. But you know, put down whatever you can. I would have only probably thought of conservation. So. All right, I think, is that it for? Did we do this one? Shows electron capture. We did do this. Okay, I think we've covered all the ones in quarks. Let me see if there are any more. Let me search the word lepton. We've done that problem. Leptons, and we've done that problem too. Okay, good. Meson, we've done that. We've already done that. Hadron. Yep. Okay, we've done all those. Let me see if there's any more Feynman diagrams. So I don't think we did this Feynman diagram. So let's do this. We did this, the first one we did, yeah. Second we ended up. Let's do this. Rhodium, 106 decays into palladium, beta minus decay, binding energy per nucleon is that, and that is that. Okay. Rutherford constructed a model based on the results of the alpha particle experiment. Describe this model. The nucleus is composed of small, positively charged, massive positively charged nucleus. Most of the mass is confined to very small, positive charge. Okay. Electrons orbit the nucleus in circular orbit. So that was the orbit the nucleus. So that was the okay. State what is meant by binding energy. Binding energy, so that's a definition. Binding energy is the energy required to put nucleons together, or no? Energy is required to, yeah. The work done or the energy required to separate all the nucleons, separate all the nucleons of a nucleus into free nucleons. That's how I would say it. The energy needed to separate the nucleons of a nucleus, good. Or the energy released when a nucleus is formed. So that's the other definition. Show that the energy released in the beta minus decay of rhodium is about 3 megaelectrons. Okay, well, so we have rhodium 106 becomes palladium PD 106. That's 46. That's 45. We need to have a beta minus to conserve charge. 1 minus, and that's 0. And then of course we have our antineutrino, electron antineutrino. Now, binding energy per nucleon of rhodium is that, and palladium is that. So we need to figure out the energy released, right? Show that that's the energy released. Okay, so change in energy, or change in energy. On the left-hand side, we have 8.521 mega electron volts, right? But then we have 106, but that's the binding energy per nucleon. So we need to multiply that by 106. And then if we subtract 8.550 times 106. So if you do minus initial, you get a negative number for release, but either way. Okay, that is going to be, now you put that 8.521 times 106 minus 8.55 times 106, and you get, oh wait, this is a negative number because I did initial minus. Yeah, I'm sorry. If you had done final minus initial, you would have gotten positive number. But this happens to be negative 3.074 mega electron volts. Let me see what the answer is. And then you could say the magnitude of the energy change is approximately 3 mega electron volts as required. Good. Okay. Exactly what we did. Okay. Now, show that we did that. Draw a labeled area to complete the Feynman diagram. As we said, the only particle we're missing is the electron neutrino, the antineutrino. And remember, this is an antineutrino, not a regular neutrino. So if we have our antineutrino on this side, the arrow needs to point to the left, because otherwise that will be wrong, I believe. Yes, because that's right. This is always confusing. It's when the time axis is on that side. Wait, no, I think that I did that wrong. Yeah, the time axis is when the time axis is on this side. We would need the anti-neutrino to go pointing this way. Yes. I believe so, and that has to be obvious. So I think it's that way. Let's check. Oh no, it's up there. Okay. I never understand how to do this. So it's coming through this way. Why is that? That's what I just don't understand. Because time is this way. Okay, if time is this way, then oh, okay. If I put it on this side, that would have meant, yeah, if I put it on this side, that would have meant that it started off that with the proton or the down quark, which wouldn't have made sense. So I think that's why it goes on this side. If we drew this on, if I drew time on this axis, then this probably would have been down quark here, becomes an up quark here, and then you have the weak interaction, and you have probably something like that. You would have probably your electron here. Electron again. The way we had done it before, well, it must be drawn upwards from the vertex in time direction, above the horizontal. So that's just 1 mark. So I guess I wouldn't have gotten that point if I'd done it initially. It has to be above. Wait, that doesn't look right. The way I did it, time on the horizontal axis. I think actually then probably be. This is very confusing to me when the time axis is switched. What would it be then? Up quark go this way. So as time passes, the down quark, I think this is what it would be. Down quark here becomes up quark. And then we would have a little squiggly for the weak interaction. And then we would have electron. We would have this way, we would have the electron. I believe that's how we would do it. Yeah. Yeah, I'm sorry for making this confusing. This is just really weird to me how this whole thing works. Okay. Yeah. So let me see if there's any more Feynman diagram questions. I believe that's all the Feynman diagrams, and then the rest are the same. All right, that's it for today. I know my understanding of Feynman diagrams is not clear yet, and I probably need to do some more practice and see some more, but hopefully this helps, and you can at least see the question and go through more time as well. All right. Bye, everybody.